For the past 39 lectures we have been looking at recovery purification of the bioproduct, be it a pharmaceutical product or be it a protein. We have to go through all these various steps for both recovery as well as purification, and we looked at large number of downstream approaches which can do this job, and we also looked at the design of those downstream, what are the issues, problems, and little bit of costing as well. Now how does this future for downstream looks like, and we will spend some time on that. How is it going to look like, how does the industry look like, what are the challenges the industries are going to face in the next 5 years or 10 years, and what is the focus currently by the industries in this area. This is very important for researchers in research labs as well as faculty working in the area of downstream, because they can focus their entire effort, their entire research in that particular direction rather than looking at various downstream processing steps. And so we are going to talk about the future trends, how the future looks like in the area of downstream processing. Now downstream processing is very mandatory for biopharmaceutical drugs, food and flavoring, because the product has to be extremely pure. That means you need to remove all the unwanted metabolites, toxins, other degradants. So it is a mandatory for all biopharmaceutical drug manufacturing, and generally most of the manufacturing in biological processes products is being managed by the contract research organization. So the downstream process market is US 1.5 billion in 2009, and it is expected to reach 3.7 billion in 2016. So you can see almost a doubling of this particular market in the coming years. Now if you look at the reagents, as you know, a lot of reagents are being used in downstream: solvents, chemicals, acids, buffers, stabilizers, proteins, so many chemicals are being used, and the market for that moving from 4,300 million in 2009 to almost 6,600 million in 2016. So that market is also supposed to grow tremendously. So you see both these markets are going to grow tremendously. So there is a lot of potential for the companies to focus on and try to improve their yields, efficiencies, try to reduce the bottlenecks or totally eliminate bottlenecks, find out new strategies so that they can work better, so that they can work more efficiently. So 48% of the US companies and almost 68% of the Western European companies, they felt that downstream processing is the capacity constraint. That means I can easily scale up my fermenter, I can easily scale up my bioreactor, there is no problem, but after the reaction or after the biotransformation or after the fermentation, I need to do this recovery and purification, and that is going to be the real bottleneck, and that is where the companies feel is going to be a real challenge. This was taken from this particular reference. It is called tracking downstream purification. Downstream is viewed as a capacity constraint now. So the companies cannot immediately increase their capacity by increasing their fermenter throughput or the reactor throughput, because the downstream purification could be the real bottleneck. So the top concerns of the industry in 2000, they felt that the chromatography purification is the real constraint. That is a real concern, because as you know we talked quite a lot about chromatography, different types of chromatographies, and the challenges in chromatography, what are the issues and so on. So you can see that is going to be a real concern for the industrial biochemical engineers as well as the industrial managers, number one. Number two, companies want to move away from protein A as an affinity chromatography ligand. I will spend little bit time later on telling you what is protein A, but protein A is a protein which is used as a ligand for purifying proteins using the affinity technique. Okay, so the companies want to move away from protein A. Protein A has been there for some time, there are a lot of issues with protein A, so they want to move away from that. So these are some constraints, some worries by the industries in the year 2000. Recently some survey was done, and the companies were asked what purification steps are creating capacity constraints. That means which step is really a bottleneck that they cannot scale it up further. Most of the survey talked about chromatography. So chromatography, that is 43% of the surveyed biochemical engineers felt that chromatography column is creating a lot of capacity constraint. 32% felt the depth filtration is the real constraint. 26% felt ultrafiltration is the real constraint. So you see, chromatography and filtration are going to be the bottlenecks according to them. Now if you rate them, or if you rank them according to the seriousness of the problem, which downstream causes bottleneck in the future, column chromatography comes at the top, followed by virus removal, followed by ultrafiltration, followed by depth filtration, then you come to tangential flow filtration, clarification, sterile filtration, finally diafiltration. So most of the concerns or serious problems start from here and go down. So if the R&D effort by the academics, R&D effort by the industrial organizations are focused here, then these bottlenecks could be overcome. But this is going to be a very serious problem. So based on this, even the academics could focus or start working on these particular problems. So nearly 2/3 of biopharmaceutical companies are spending lot of money for acquiring new downstream processing technologies. So as I said in the beginning of the talk, that downstream is going to be a real bottleneck in the next 5 to 10 years when compared to the manufacturing. So many companies are spending a lot of money in the downstream technology so that they could overcome this particular problem. Now where are the companies thinking about spending their money? Inline buffer dilution systems, that means can I dilute as the process liquid flows through inline. Single use filters, that means can we filter and then throw the filter out. High capacity resins, that means resins which have very high capacity factors. Single use disposable tangential flow filtration, that means if I use a single use system, I do not have to worry about sterilizing after use, I do not have to worry about contamination because of the previous batch. So single use disposable filters. Online analytical and control, that means as the fluid flows in a manufacturing plant, can I measure the compositions, can I measure the various parameters online. Disposable ultrafiltration systems. Alternatives to chromatography, as you know, chromatography is extremely ubiquitous, it addresses different aspects of the physicochemical properties of the protein, and it can use for recovery. So are there any alternatives for chromatography? Buffer dilution systems. Membrane technology is a very big area because there are large number of membranes which are used at various stages in the filtration and recovery process. So looking at membrane technology, centrifugation, moving bed precipitations, the development of monoclonal antibody fragments, two-phase systems, that means you have solvent and buffer or aqueous and organic layers, countercurrent systems, countercurrent extractions, countercurrent absorptions, and these sort of countercurrent systems. So all these are areas in which companies are thinking about investing, companies are thinking about buying technologies, companies are worried about in the future. So as this happens, we definitely expect that there is going to be a lot of improvement in membrane processes, monoclonal technologies, specialty resins in chromatography column, synthetic affinity matrices. So they will be very close in cost to protein A, so that they are going to be a real alternate instead of protein A. Now what is protein A? Because I talked about protein A, so couple of slides I will talk about this protein A. Protein A is a 40 to 60 kilodalton microbial surface component recognizing adhesive matrix molecule, that is MSCRAMM. So it is a surface protein. It was originally found in the cell wall of Staphylococcus aureus. Okay. So protein A is 40 to 60 kilodalton microbial surface component recognizing adhesive matrix molecules. So it can be used as an affinity ligand. Okay. It is encoded by the SPA gene and its regulation is controlled by the DNA topology, cellular osmolarity and so on actually. So it is an adhesin protein, it mediates the initial attachment of bacteria to host tissue leading to infection. So this protein A is a surface protein, it helps in the attachment of the bacteria to host tissue leading to infection. Okay. Now protein A binds with high affinity to human IgG, that means immunoglobulin G, okay, and it also binds very well to IgG2 and also mouse IgG2A as well as IgG2B. So if I immobilize protein A on a solid support, I can use it as a affinity ligand to capture IgG, human immunoglobulins, right. So I can use it for purifying immunoglobulins from crude protein mixture such as serum or coupled with one of the above markers to detect the presence of antibodies. So it is very useful. So I can capture the immunoglobulin from blood serum by having protein A immobilized on a solid surface. So protein A acts as a ligand here. So protein A technology has been very useful in purifying serums and other crude protein mixtures for getting human IgG1, human IgG2 or mouse IgG2A or mouse IgG2B. So are there any alternates to protein A so that the problems that are now associated with the protein A could be overcome, and that is what I think the future chromatography, ligand based or affinity based chromatography is going to look at. So what is happening in industry currently? There are many things are happening and I am going to show the next few slides talking about what some of these industries are working on based on their own R&D effort. Single use downstream chromatography. Okay. So Novozymes is working on single use downstream chromatography, that means they will do the chromatography and throw it away. So the problems of sterilizations, problems of cross contaminations are completely overcome. New patented dual affinity polypeptide technology which will replace protein A but disposable technology, that means single use approach. So Novozymes is working on that. Now if you look at another company called Millipore has been there in purification and filtration system. They are looking at stimuli response polymers. These polymers will enable complexation and manipulation of protein, okay, and allows for control of polymer and protein complex solubility. So they are working in this type of new polymers which will help in binding certain proteins. So this can be used as a direct capture of product without going for centrifuges or protein A type of media actually. Mixed mode absorbance to replace traditional protein A and ion exchange for better selectivity. Okay, company like PAL Corporation, they have a product called MEP, hypercell mixed mode. Okay, so they are working on certain media which includes hydrophobic charge induction chromatography, that means it does not have salt and can capture mono or polyclonal antibodies. Another company called BIA Separations, they are working on monoliths involving chromatography medium as a single piece homogeneous column. Okay. If you look at another company called Tarpon Biosystems, they are looking at simulated moving beds which involves multiple columns in a countercurrent chromatography. So you have many columns and the liquid flows in certain pattern into different columns so that it simulates the moving bed principle. Another approach, protein G, this is a single domain camel derived antibodies for IgG that is being looked at by a company called Prometic Bioscience. Another company called Upfront Chromatography, they are looking at expanded bed adsorption chromatography systems. Okay. Then there are a lot of technologies that are being looked at by several small and medium sized companies. For example, company called Zircon Separations, they are looking at ultra durable zirconia oxide bound affinity ligand. So they are looking at inorganic type of base material for especially for ligand chromatography media. Another company called NISA Membrane Technologies, they are looking at membranes, alternate membranes, new modified membranes for separations. Okay. Another company called Pure Farm Technologies, they are looking at membrane affinity purification system. If you look at Prometic Bioscience and DAX, they are looking at custom designed ligands for affinity chromatography. Invitrogen and Dynal, they are looking at coating magnetic beads with protein A and protein G. Okay, so the magnetic beads could be manipulated by an external magnetic field, but these magnetic beads will be covered by these protein A and protein G affinity ligands. So these are some ideas that are being looked at, technologies being looked at, and they may come into market in the next 2 to 5 years. Roche, they are looking at affinity purification methods based on expression of proteins, okay, affinity chromatography media, histidine tag media, and so on. And then there is a lot of work that is being done on protein A alternates, including reverse micelles, liposomes, liquid extraction systems, crystallizations, immobilized metal affinity chromatography, novel membrane chromatography. So all these are separation techniques, high selectivity techniques, which are meant to replace the ligand based affinity chromatography. And then disposable equipment, that is going to be the future, single use equipment or disposable equipments in commercial scale production. That means I may have a 1000-liter disposable bioreactor, I may have a 100-liter disposable system, filtration system. So you use it once and throw it out, so you do not have to think about sterilizing this material, you do not have to think about contamination from the previous batch or contamination that will happen to the next subsequent batch, and so on. Actually completely modular design, that means you will have bits and pieces of all the downstream all connected like a Lego piece, mobile biopharmaceutical operation. So I can move my filter to wherever I want, I can move my chromatography to wherever I want, they are not fixed with hard pipes, you can have flexible pipes, so you can move the chromatography before a downstream operation, or you can move it after, so depending upon the type of process you are looking at. So that is called a mobile biopharmacy. And plug and play solutions, okay, so we can connect different parts or different aspects of the downstream and make a complete downstream process technology. Okay. So companies like Acta Avent, GE Healthcare, they are also looking at this type of plug and play solutions even for design of experiments, which is a very important statistical tool for optimizing the processes, looking at multi-component, multi-column continuous capture plug and play solutions. So these are some more approaches that are being looked at in the near future to come. So according to Robert Blank, bioprocess strategic marketing manager of Millipore, the future direction is going to be integrated disposable process solutions. Okay, so it is going to be integrated and disposable. It may have bioreactors, it may have chromatography, it may have tangential flow filtration, it may have virus filtration, sterile filtration, buffer media storage, intermediate handling. So you see all these different parts, and it is going to be integrated, it is going to be like a moved around, and it could be a disposable sort of setup. So you may have a reactor and all of them may be put all around it, and all of them can be thrown out. And as I said, large scale disposable reactors, vessels, storage, buffer media storage vessels are already coming into market for manufacturing, and so the fixed large scale equipments may soon disappear. So what are the future changes in downstream appear to be in? So there is going to be improvements, there is going to be efficiencies, there is going to be modifications in some of these areas, affinity chromatography, because that is going to be the most important area where we are talking about getting 100% pure protein product for therapeutic applications, alternates to protein A, new packing materials, virus filtration, because once you complete your cell breakage and recovery protein, one of the problems that could be still is the contamination of the viruses. So can I completely eliminate the viruses from the therapeutic proteins which are obtained from these viruses? Cross flow membrane filtrations, simulated moving beds, single use disposable, that means you do it once and throw it away, so you do not have to bother about sterilizations and so on. Plug and play, that means you connect two different downstream one after another and then you immediately start using it. So the commissioning time is reduced dramatically by this type of approach of plug and play. So these are the areas in which we are going to see a lot of changes, because these are the areas which have been giving considerable problems during downstream, and these are the areas which are giving considerable bottlenecks if you want to scale it up further. So all the research by the industries are being focused in this particular area, and so if the academic research also focuses here, it will be very useful for these industries. So the most important, as we can see from this list, is the chromatography and the filtration. These are the two, and the recent advances or the recent concept or recent thinking is in the area of single use disposables. That means you do it and throw out the equipment, you do not have to think about sterilization and so on actually. Okay. So with that we come to the end of our the past 40 lectures of downstream processing, and it is the most important set of operations which help you to recover, purify the desired biological product. That means a product which is derived from bacteria or fungus or any other biological source. So it is one of the most important steps that is mandatory if you are manufacturing a biopharmaceutical product, because the purity of such a product is extremely important, and downstream process also decides on the cost of the final product, because more number of inefficient downstream steps you adopt, obviously the selling price of the product goes up, and you may end up having an uneconomical product entering the market. So downstream process plays an extremely important role in the final cost of your desired product. It determines the selectivity, it determines the purity as well as the cost. So having said that, we mentioned that it is very important for recovery and purification of biosynthetic products, that means products which are made from biological origin, pharmaceutical products, that means drugs, whether it is a chemical based drugs or whether it is a biological based drugs, okay. Pharmaceutical, food, large number of food, fermented food and processed food are now being made using biological fermentation approaches. Chemicals, bulk chemicals like acetic acid, specialty chemicals, surfactants, biopolymers are all currently being made using biological techniques. Health and nutraceuticals, and again health and nutraceuticals has become very important of late, and they are also being made using biological origin through fermentation or through natural products. So you are going to have a downstream at the end of a fermenter or a enzyme reactor. Without a downstream you cannot directly use the fermented product for commercial use. Okay. So after the fermentation or biotransformation, the desired product is present either inside the culture or in the medium or in the broth. Okay. So your goal is to recover that and purify that, whether it is inside the culture cells or outside in the media. Generally the concentration is going to be very low, 5 to maybe 25% max, but you would like to bring it to 90, 95, very close to 99, and if it is a pharmaceutical product you want to make it 100%, and that is where the downstream processing technologies, processing approaches which you have been talking about in the past so many lectures become very useful. So this is the slide which I showed almost 40 lectures back, remember, I hope you all remember this slide. This is the heart, you have the reactor or a fermenter here, and whatever is on the right hand side we called it as the downstream, and whatever on the left hand side we called it upstream. So you are preparing your biocatalyst, you are preparing your media, sterilizing your media components, inoculation, little growth of the organisms, and immobilization of the enzymes, all these come under the upstream. Now here you have the downstream. So here we are talking about recovery of your product, and then purifying your product, and then stabilizing your product. At the same time you are going to get some side products, then you are going to get a lot of waste. So I briefly talked about effluent treatment plant here as well, but that itself becomes a big subject to talk about, but we just covered very briefly on various effluent treatment, be it solid, be it liquid, or be it gaseous effluent. So all these come under the area of downstream. So in the recovery sometimes you recover raw materials, sometimes you recover enzymes, sometimes you recover active biomass which you send it back for the next batch, thereby you reduce the cost of the final product. In the recovery section the concentration of the initial product will be very little, concentration of the final product will be very little. So you are trying to improve the concentration to a larger value, and then finally you are trying to purify it to almost 100%. Okay. So this is where you have the types of filtrations, you have the type of chromatographies, you have type of crystallizations, and so on actually. So what are the main steps in the downstream we talked about? Separation of the cells or the biomass. So as soon as your liquid broth comes out, the broth contains biomass, cell debris, salts, other floating undissolved material, and so on actually. So here is the first step where you are separating them out. If your desired product is inside these cells, that means if your product is intracellular or if it is in the periplasmic, obviously you are very much interested in the cells, but if your product is extracellular then you are not interested in the cells, you recover the cells and throw them out. Okay. So if you are interested in the intracellular material, obviously you will be doing the disintegration of the cells. So we looked at large number of techniques, physical based, mechanical based, chemical based, enzymatic based techniques for disintegrating the cells and getting your product out in the media. Okay, once you get this product, it is going to be a very dilute solution. So you first try to separate it from rest of the material like the side products, metabolites, toxins, and so on. Then you concentrate it, and then finally you purify it. Okay. So you purify it to the required degree. If it is a bulk chemical, purity is not so important, but if it is a pharmaceutical, the purity is very important. And finally you go into drying. Different types of drying we talked about: normal heat based drying, lyophilization, spray drying, drum drying, and so on. And then you have the desired product at hand. So these are the different steps in the downstream we looked at. So removal of insolubles, separation of cells, cell debris and other particulate matter from the fermentation broth. Then the product isolation, we said removal of water and other impurities, then you are concentrating your product, you are talking about extractions, you are talking about different types of membrane filtrations, and then purification. Here we talked about again some sort of a membranes, then chromatography, different types of chromatographies, then we looked at crystallization, we looked at lyophilization, and finally the product polishing. You are doing the drying and then you are adding some stabilizers to keep the product from degrading or getting disintegrated, so that is called the stabilizing. So all these are the various downstream steps, and I hope you remember the various techniques we covered in the course of these lectures. What are the salient features, what are the design parameters, what are the different types of designs available, and so on actually. So removal of insolubles, we looked at filtration, centrifugation, microfiltration, nanofiltration, so many different types of filtration we looked at. And even under filtration we looked at centrifuges, different types of centrifuges, drum based filtration, leaf filtration, plate and frame filtration, and so on. Under centrifuge we looked at disc based centrifuge, ball based centrifuge, okay. So many different techniques are being used for removing the solid and the liquid. Now isolation of the product, if you look at the isolation of the product, you recover the solid biomass and then you are doing the cell disruption if it is an intracellular material, and then you are doing extraction, you are using a solvent to extract your desired product from a large mess. Then you are using adsorption. So in adsorption what do? You are using a solid matrix to absorb the desired product. Then we can also use ultrafiltration. Precipitation is another technique which can just precipitate out your desired product from the broth or the mother liquor. So you would have concentrated your product from maybe about 5-8% to almost 70 or 60%. Then you go for product purification, that means you are increasing it to 90 or much higher than that. There comes your chromatography, size exclusion chromatography, hydrophobic interaction chromatography, ionic chromatography, affinity chromatography, and so on. So all these chromatography in various stages you use and bring or increase your product purity to a very high level. Then finally comes your polishing, that means you are using crystallization to get solid beautiful looking crystals if that is desired by your customer. In some cases product will be in the form of a liquid, but in some cases the product may be in the form of a solid, like some proteins could be in the solid. So you do crystallization, then you do drying, which is by heating, and then you do lyophilization, different types of approaches by which you remove the water that is present so that the product becomes stable, and then you sometimes add stabilizers, okay. You add stabilizers so that there is no disintegration or biodegradation of the final product. So the transportation or the shelf life is increased by this approach. So what are the topics we covered? We covered a wide range of topics, starting from what is the basic of a downstream. I mentioned a few case studies, we looked at some flow sheets, and then we went into costing, okay. We talked about what is payback period, debt present value, what are the cost factors that are involved in deciding on the plant cost and also on the operating cost. This is very important. You may think why should I learn about costing, I am a biochemical engineer, but then this is very important if you are going to select different types of downstream. Should I have a filter or should I have a centrifuge, should I have an extractor or should I go for a chromatography. So when you start deciding or when you start thinking, then cost plays a very important role. That is why we briefly talked about different approaches of costing. Then we looked at the cell culture, the product. is it an intracellular or an extracellular product, different types of cells, and what are the issues involved if you are trying to recover an intracellular product from a bacteria or from a yeast and so on. So different disrupting techniques, we talked about the mechanical based techniques, the enzymatic techniques and chemical methods, and also we looked at briefly the advantages, disadvantages of each one of them, and which one looks good, but at the same time which is more expensive than which technique. So we spent some time on that. So the pre-treatment strategies become very important. Should I heat it or should I cool it, so that I can achieve the breakage of the cell membrane and the release of my desired product. Okay. Then we went into the solid liquid separations, a large number of solid liquid separations based on filtration and centrifugation. Then the important equations, design equations involved in that. Then we looked at adsorption, that means adsorption of a solute to a solid matrix. What are the different types of mathematical relationships which relate the solute in the liquid phase with the solute in the adsorbed phase, and how do you calculate the amount of adsorbent required to adsorb a particular solute. Then we went into liquid extraction. This is a very important downstream processing tool or technology, because it is done at room temperature, so there is no deactivation or denaturization of the product. So we looked at counter current liquid extraction, we looked at multi-stage liquid extraction, we looked at cross flow type of design, and then we did some problems to determine how many stages are required to achieve certain separation efficiencies, or given the number of stages can you tell what is the efficiency of the entire system. So we looked at that. Then we went into membrane separations, different types of membranes, starting from ultrafiltration membrane, nanofiltration, microfiltration. Then we went into reverse osmosis. Reverse osmosis is a very important membrane technology if you want to have potable water. Then we went into other membrane operations, the dialysis, the electrodialysis, and then finally we also talked about pervaporation. Pervaporation is a combination of permeation and vaporization, so it is not based on size of the particles and filtration, but it is based on the affinity of the solute with the membrane material. So the technique is very different. So you can really concentrate fruit juices at room temperature, okay, or very low temperature, so that the fruit juices or food and flavoring material does not lose its flavoring activity. Then we went into precipitations of proteins, various types of precipitations, because precipitation is one of the methods for product recovery from a big mother liquor. So we talked about using solvents as a media for precipitating, we talked about salts, we talked about polymers, electrolytes as precipitating media, and mostly precipitation is used in the area of protein purification. Then we went into chromatography. Chromatography is the biggest area of our research in downstream. Different types of chromatographies, the principles, how interaction between various solutes affect the separation efficiencies, how to calculate the retention time, how to calculate the theoretical plates, how to calculate the efficiency of chromatography. All these were discussed over several classes, and we also looked at many problems on that. Then we spent considerable time on the analytical tool HPLC. So this is also a chromatography, but we spent some time. HPLC is not used for separating, HPLC is not used for separating and recovering like a downstream, but it is used in the area of analytical tool for identifying a particular component as well as quantifying a particular component. Because HPLC is very important, we spent a couple of lectures on different types of HPLC techniques and what are the factors involved in achieving a good separation, and what does selectivity means and what does retention time means and so on actually. So HPLC is nothing but high performance or high pressure liquid chromatography, and we spent some time on the normal phase HPLC as well as the reverse phase HPLC. Okay, then we went into crystallization. What are the approaches by which one gets a solid crystal, and what are the factors that affect crystallization and so on. Then we come to the recovery, product recovery, product stabilization and product polishing techniques. The distillation is used if you want to recover the solvents that are used in extractor, or if you want to recover the solvents that are used in the chromatography. You cannot throw those solvents, so obviously you need to recover them, and there may be more than one solvent or metabolite present. So distillation is a technique used for boiling out the desired solvent from a mixture. Then we went into drying. Drying is used for the removal of moisture from a solid product. Drying is not used if your protein or bio product is temperature sensitive, so you have to be very careful. Different types of dryers we looked at. We also looked at some equations which are involved which characterize this drying process. So if your product is temperature sensitive, then the best technique to go for is lyophilization, that is you cool it down, convert the water into solid ice, and then you remove the solid ice as the vapor, thereby you are avoiding the liquid water stage. That is called lyophilization, and it is very good if you want to really remove water from blood plasma or other highly temperature labile bioproducts. So lyophilization is another technique which we spent some time on, and then we briefly talked about stabilization of bioproduct. So how do you stabilize a bioproduct so that there is no degradation, there is no degeneration of the product, or there is no bacterial growth or fungal growth, because all these bioproducts need to be kept for considerable amount of time before they are sold in the market. So the products should be stable in the manufacturing side. So stabilization of bioproduct is also an important downstream which needs to be considered. Then we talked about absorption. Although it is not a direct downstream, the gases that are leaving a fermenter cannot be directly vented into the atmosphere, because it may contain toxic vapors or dangerous gases which cannot be exposed to the flora and fauna. For example, carbon monoxide or SO2 or SO3 or chlorine. So absorption is a technique which is adopted to recover or capture all these gases before the inert gases are vented into the atmosphere. So absorption is based on a bulk technique. So you use either alkali, mild alkalis, you may use water, or you may use ethanolamine. These type of chemicals will absorb the gases which should not be vented out in the atmosphere. And then very briefly talked about some effluent treatment techniques and what are the various stages in the effluent treatment. Then in order to run a downstream manufacturing plant, you need a lot of utilities. You need air, you need water, and you need steam, high pressure steam, low pressure steam, you need chilling water, you need cold water, and so on. So utilities are very important, number one. Number two, utilities add to the selling price of the product, because utilities add to the working capital. So managing the utilities is also very important if you want to keep your cost of the downstream step low. So utilities are very important, and depending upon the complexity of the downstream, the number of utilities may be very high. So a downstream process may be having just water as utility, whereas in some other places you may have chilled water, cold water, steam, air present. So utilities add to the overall selling price. We also spent some time on another analytical tool that is called the electrophoresis, and SDS page. Although this is not used in the downstream manufacturing, it is used as an analytical tool for separating proteins and also for identifying proteins based on the charge on the proteins, based on the isoelectric pH of the proteins, based on the size. So we did spend maybe a class on this particular analytical tool, that is the electrophoresis and the SDS page, although they do not come directly under as the downstream. So we spent some time, little bit time on two analytical tools. One is the HPLC, which is extremely important in separating, identifying and quantifying proteins or biomolecules, and electrophoresis and SDS page, which again can be used for separating proteins, identifying proteins based on the charge, based on the mass. So these are the two analytical tools which are very important, which we talked about in the past 39 lectures. Okay. So to conclude, would say downstream process, it is a highly interdisciplinary subject. It connects engineering, as you can see, the biochemical engineers, chemical engineers are needed. It connects engineering with protein chemistry. Lot of proteins are being looked at, chromatography, separations, SDS page, HPLCs, all these are involves protein. It connects biologists, okay, so because you have a lot of biological tools and techniques. It connects analytical chemists, because we are talking about analytical tools like HPLCs and electrophoresis, and the biochemistry, because there are a lot of biochemical assays involved in downstream processing. So it is a highly interdisciplinary subject. It connects a large number of principles, starting from engineering to chemistry to biology. So I do not think one expert will be able to manage a large plant of so many different techniques, and it may require a team of biologists or protein chemists or engineers to solve the problems that are faced actually. And the economics of the entire bioprocess is completely governed by the downstream processing technology. As I said, the cost of the product is highly dependent on how complicated is your downstream, because I showed you many flow sheets where in some flow sheets you have so many chromatographies and so many filtrations that the downstream contributes almost 50-60% of the cost. So the entire cost of a product depends on the downstream process technology. So you can spend a lot of effort in improving the process efficiency, improving the selectivity, so that the cost comes down. Usage of solvents can be brought down, usage of the large scale equipments can be brought down, that means trying to use smaller equipments, usage of the utilities like steam or water can be brought down. By doing all this, you are reducing the working capital as well as the overall final selling price of the product. So this completes the course on the topic downstream process in bioprocess technology. I hope you enjoyed the past 40 lectures. It was in some area, sometimes it was given as a very broad spectrum. In some places we went quite deep into the fundamentals, looking at the physical principles involved in arriving at certain separation techniques. So as you can see, it appears to be a combination of some of the chemical engineering steps like distillation or absorption or extraction with the biochemical steps like chromatography. So it is a mixture of both the chemical engineering as well as the biochemical engineering, and that is what is downstream processing is made up of, and that is what makes it very challenging for engineers as well as the biochemists, protein chemists as well as the biologists.